Welcome back, guys. So in the previous video we saw about the potential energy stored in an electric dipole, and now we'll go ahead with the this video is going to be just like a reasoning video. We are going to be talking about the characteristic features of conductors, their electrostatic properties. So there are mainly 5 points under this. First I'll write down the points and then we'll discuss each point briefly. Okay. So these are the 6 points of electrostatics of conductors. The first one is, inside any given conductor, the electric field or the electrostatic field is going to be always 0. The second one is, at the surface of any conductor, the electric field must always be perpendicular to the surface. This is very similar to the concept of equipotential surface, which we have done the second video of this chapter. And then the third point is, the interior of conductor can have no excess charge. The fourth is, potential is constant throughout the interior and is equal to the value at the surface of the conductor. This is the value for electric field at the surface of any given conductor. And the last one is electrostatic shielding. This is a property of a conductor. Okay, so now let's quickly see all of these one by one. So the first point is, inside a conductor the electric field is always 0. So let's see why is this true. So let's consider this to be a conductor. It could have been of any shape, but I've just chosen it to be a box so it's easier. And these are the negatively charged electrons. There are also positively charged protons, but we are just talking about one at a time, but it doesn't make a difference. So in the static condition, that is when there is no electric field, both of them are opposite to each other. There is no electric field over here. They cancel out and overall it's neutral. So there is no electric field anyways. This is the most simple case. But in the second case, that is when there is an external electric field, let's consider the electric field to be in this direction. So now what happens is, if there is an electric field, should there also be an electric field inside? How can the electric field be still equal to 0? So now let's see what happens. As I told that the left side, or from where the electric field starts, is termed as the positive side, and the right side where the electric field is tending to go towards, that's the negative side. So all the electrons present are going to get attracted towards the left side of the conductor, because positive and negative attracts, and all the protons, positively charged or positive charged ions, any ions which are positively charged, are going to get attracted towards the right side of the conductor. So you're going to have a situation like this: negative, 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 and positives over here. So now what happens is, this is no more neutral charged conductor. It's not similar to the static situation. Now there's going to be an electric field induced in this direction of equal magnitude to the one of the external condition. So these two electric fields, being equal in magnitude and opposite in nature, cancel out, resulting in a net 0 electric field in the interior. So this is how inside a conductor electric field is always 0, whether an external field is there or if it's not there. So now let's look at the second property. So let's take a shape of a conductor. Let's assume it to be a sphere in this case. So this one states that at the surface of a given conductor, the electric field lines must always be perpendicular to the surface at that point. So this has to be true because we have discussed, this is the same logic as what we discussed for the equipotential surface. When there is a perpendicular force, it does not contribute to work done. You can imagine it in this case. Let's say there is a block which is fixed along the ground, and you are applying a force in this direction to try to move it in this direction. There is going to be no work done. And this is why work done equals Fs cos theta, where theta is the, this is the displacement we require, and this is the force. It's at an angle of 90 degree. And cos 90 is 0, and this is why perpendicular forces do not contribute to work done. And that is exactly why we require a perpendicular force, and there should be no component of tangential force, of any force lying along the surface. If there was a case where this is not there and the given force is like in this direction, we saw previously how to do it. We can resolve it along the horizontal and the vertical components. This component of the perpendicular force is the one we previously discussed, and it's not going to contribute to work. But however, there's going to be a horizontal component which this gives rise to this vector, which is going to cause a force on the external surface. This is going to cause charges to move. We saw that in a conductor, the positive charges always lie on the exterior surface, on the outer surface. So this is now going to cause these charges to move, giving rise to a current, and this is no more in the static situation which we require. So again, electric field must always be perpendicular and not have any tangential component. This is the second point. Now let's go to the third point. Okay. So the third point is the interior of a conductor can have no excess charge. And this is true because the property of a conductor is that all its charges lie on the outer surface. And this proof is not given, so we do not have to learn it for now. It's just a property of conductor to keep in mind, that all the charges reside on the outer surface. So they cannot have any excess charge in the interior of a conductor if it needs to be in a static condition. If this rule breaks, then you cannot consider it to be an electrostatic property of a conductor. Okay, so there's not much to explain in this point. Let's go to the fourth point. Okay, so the fourth point was that the potential is constant throughout the interior and it has the same magnitude, the value, as the surface. That is, let's again consider a circle. It's easier to deal with. That means, let me name 3 points, A, B, and point C. Potential at A equals potential at B equals potential at C. This is the condition. That means if you have to move a charge, positive charge, from here to here, you do not need to do any work. Work done is zero because we know work done equals potential final minus potential initial. These two potentials are the same magnitude. So work done equals to zero if you want to move any charge between inside the interior or also to the surface and from the surface. The work done is all same, zero. The potentials are all same. And this is the thing, that potential is a constant. And this directly implies from the first formula that electric field inside a conductor is zero. So when there is no electric field, there's going to be no force to oppose. It's all free space. There's no force to oppose. Then what do you have to do work against? So hence work done is zero. Let's go to the fifth point. Okay, so the magnitude of electric field at the surface of any conductor is sigma by epsilon naught. There is a small proof. If you want to learn the proof, you can, or else you can directly skip to the next point, and I have written the timing over here. This proof is not very important to be remembered, but the point is important. It can come as an MCQ, but here's the thing, the derivation is very simple. It's very similar to the formula for electric field due to a plane sheet. It's almost the same thing except there's only one surface. So let's see how it's different. Since this is a conductor, you can take it to be in any shape. Like in the textbook, they have taken it to be a shape like this, which could make it confusing. So I'll just take it to be a plain sheet again. But there's a difference. Let's think of it as a rectangular slab, which is a conductor. This is the conductor. And I'm taking only one of the faces to do the derivation. That is, I'm taking only the top face. That is a rectangle. If the entire thing is a conductor, that implies this is also the surface of a conductor, right? We need to deal with the surface. We are not talking about the interior, we are talking about the surface. So any surface of this conductor is going to be one of its faces. So now, the property of a conductor, if you remember, is that the charges lie on the outer surface. That means charges are not under the plane, they are above the plane only. The charges are over here. In the derivation for electric field due to a plane sheet, we considered the positive charges on either side, so there was an electric field downwards as well. In this case, that's not what's happening. In this, there is only electric field in the upward direction. This is how it is. Now we can apply Gauss's theorem. So you need to construct a Gaussian surface, and let's again consider it to be a cylindrical face. in this way. If you can clearly see the difference, that over here what's happening is, last time we considered the phase to go even downwards because there was the electric field down. But now there is no electric field down, so we are just dealing with the top. So let's consider this is the point. So what is Gauss theorem? On the left hand side of the Gauss theorem, you had E dot S, electric field times the surface area of the Gaussian surface enclosing. Let's consider this to be S and this to be S. What is the total flux? That is the first step, right? Let's do it stepwise. Steps is find the total flux. First one, flux total is equal to, there's only one flux over here, which is this. There is no flux in the side because the electric fields are along the direction of the curved surface area of the cylinder. We have discussed this in the same video. So total flux is going to be flux due to this surface circle, due to the top circle, that is equal to E dot S. I have considered the surface area to remain as S. So this is the total flux. And now step 2 is to equate with Q by epsilon naught. But here what is Q? Q is the amount of charge that is lying inside the Gaussian surface. This entire thing has a charge of Q, but how much will be present in this small surface? Again, we are using the concept of surface charge density. You can refer with this once. You see a sigma over there, that means there has to be a sigma somewhere over here. So surface charge density is equal to Q divided by the entire area. So in any region you want, the charge stored over there is going to be sigma into A. But in this case, the surface area of the top equals the surface area of the bottom. That is the same as this S. The reason I am doing it very quickly is because this is the same step we have done in the previous one. So you can first watch that video and then come to this. So Q equals sigma S. So equating these two equations, E dot S is equal to Q sigma divided by epsilon naught. And we get that electric field equals sigma divided by epsilon naught. This is the electric field in any surface of any conductor. So this is the fifth point, and let's look at the last point, which is just one of the properties. It's not any theorem. Okay, so this is about electrostatic shielding. And you can clearly see the word shielding. That means you're protecting something from something else. So what are you protecting? You're protecting any instrument that's of great importance. It could be an electrical sensitive material which you have to keep it away from electric field. So what you do is you make use of the property of conductors. That electric field inside a conductor is zero. So when you have a conductor and you are keeping some material over here which is of your importance, you have to make sure this is not exposed to external electric field. You place it inside a conductor, so the conductor has all its charges outside. The electric field inside is going to be zero. You are shielding the material from the external electric field, and that is what electrostatic shielding is about. It makes use of the property that conductors have zero electric field inside at any given condition, whether there is a field outside or even if it's not there. So these are the properties of electrostatics of conductors, and I'll be ending the video over here. In the next video, we'll talk about polarization and about what are dielectrics. And after that, we can start with the second part of the chapter, which is capacitance. It's a small part. So there is one direct application of this, which is called the Van de Graaff generator. So over there, we'll clearly see how electrostatic shielding has practical, like industrial applications. Okay, so thank you. See you all in the next video.